All right, let me start by again thanking the organizers for putting this meeting together and for ICTS for providing a fantastic venue for it. Maybe I'll start by writing this title on the board. You will notice from the title that this part of the meeting is supposed to have something to do with automorphic forms, but there are not explicitly any automorphic forms in this title, and there will not be any automorphic forms explicitly in this talk. That said, I'm hoping that what I'm talking about is applicable to automorphic forms via other mechanisms that we already know relate things like phi gamma modules to automorphic forms, things like eigenvarieties and so on. So in some sense, this talk is more of a continuation of my lecture series from last week than a separate talk in the conference, but I hope it will be informative nonetheless. So in particular, since this is a continuation in some sense of my lectures from last week, I will be using some concepts that, if you were here last week, should now be quite familiar. If not, lectures from last week are recorded, so you can remind yourself about things. I also have some notes from my lectures from last week, which you can find on my website. And I should maybe mention right at the outset that all of this work comes from my long-running joint project with Rochuan Liu, which includes one asterisk volume and some other papers that are in progress. So everything is somehow taken from that project. Okay, so let me start with the picture that I set up last week and briefly set the relative version up as well. So I'll say more about the relative version today. So just as a quick reminder, if F is a perfectoid field of characteristic P, which for the moment you can, if you don't remember what a perfectoid field is, you can think of a complete algebraically closed non-Archimedean field. But in fact, it really just has to be complete and perfect. But the algebraic closed case is a good example to keep in mind. I'll make some reference to it. Then there's a construction due to Fargue and Fontaine, which gives some kind of geometric space associated to this. Actually, it gives two geometric spaces associated to it, which I was notating XF and XFN, where XF is is a scheme which is it's some sort of what they call an abstract complete curve. So that means that it's Noetherian of dimension 1, regular, I guess I should say it's connected with scalars being QP. So the global sections form a field. That's another part of the condition. Separated, I should have said. And there's a degree function on divisors which factors through the Picard group. So you have a well-defined notion of degree of a divisor. Every effective divisor has a non-negative degree. If you're in the case where F is algebraically closed, then every closed point has degree 1, and otherwise there are some finite extensions involved. But so you have something which looks one-dimensional. You have a notion of degree. So you have initially you have a formal theory of vector bundles that behaves like it does on a complete, a proper curve or a complete Riemann surface. And then it turns out there's even more into that analogy, but let me come back to that. So the XFN is some kind of non-Archimedean analytic space. The right context in which to work with it seems to be Huber's theory of adic spaces, which we had some lectures about last week as well. I mean, right, if you're not familiar with adic spaces, they work sort of like rigid analytic spaces, but they're not built out of Tate algebras. They're built out of some more general Banach algebras over QP, or over F, I should really say. No, these are over QP. This is over, yeah, this all happens over QP, even though I start with some field characteristic 0. Sorry, I start with some field of characteristic P and I get something over QP. So this analytic space can be written in the following way. So A-inf denotes the ring bit vectors of OF. So this is a perfect ring of characteristic P, so its vit vectors behave well and give you something which has OF as its mod P reduction. So this is morally power series in P with coefficients in OF, except you have to make that make sense. And you do that by putting some exotic ring structure on sequences of elements of OF. And you get, in this case, you get a local ring whose residue field is the same as that of F. So this thing you can topologize using, well, you can't quite take the topology generated by the maximal ideal because the maximal ideal is not finitely generated. This ring is not Noetherian and has other failures of finite generation properties. But for the purposes of writing down the topology, you don't really need to take generated of the maximal ideal. It's enough to take some finitely generated ideal that is primary. So you could take, for example, the ideal generated by P and the Teichmuller lift of some element of the maximal ideal of F, OF. So, and of course, the topology is not going to depend on this choice because any two choices of the ideal are cofinal to each other. So if you want, now that you've topologized this ring, you can use it as a Huber ring and you can form its adic spectrum, except what I really want is to take, I want to take out the 0 locus of P and this var pi bracket, because then I can take a free quotient by the action of Frobenius. So the fixed locus of Frobenius is precisely, so there's a picture that you see sometimes where SPA of ANF sort of looks something like this, except it's not really, drawing it as two-dimensional is a little bit misleading because it's somehow really more like this. That there's, maybe I shouldn't try to draw this picture. Yeah, so there's sort of a point over here, which is P equals 0. There's a point over here, which is pi equals 0. There's a generic point over here, which is, well, generic is the wrong word because it's a closed point. There's another point sort of sitting over here, which is where they both vanish. And once you take these out, then the action of Frobenius, of course, it fixes P and it changes and it raises this to its pth power. So it kind of, this is an accurate picture up to homotopy, and at the level of homotopy types, you can conceptualize this as just taking every point and sort of sliding it some discrete distance over, well, discrete in the multiplicative sense. And so what ends up happening is that you get a free quotient, you get a free action of phi, it's even properly discontinuous, so you can take the quotient to get a space like this. And then xf you can think of as being proj of a certain graded ring, where pf is a direct sum of graded pieces, where the nth graded piece is the sections of some line bundle O of n, where O of n arises from the phi equivariant line bundle on, if I call this thing YF, the part before I take the quotient, well, YF is basically contractible, so it makes sense to talk about trivial line bundles on it, but with some non-trivial action of phi. So if I have one generator which I call E, then I want the action of phi of that to be p to the minus n times E. So if you're used to seeing the definition of the Fard-Fontaine curve, where this thing is like the phi equals p to the n invariance of B Chris, then that turns out to be the same thing as this, but you have to do some calculation to check that. But this point of view makes it easy to see that there is in fact a morphism of locally ring spaces from here to here, and this morphism satisfies Gaga for coherent sheaves. So it behaves like an analytification morphism between, say, a complex scheme locally of finite type over C and its complex analytification. You have a morphism from the analytic version to the schematic version, which has the property that pullback of coherent sheaves from the scheme to the analytic space is an equivalence of categories and preserves coherent cohomology. So that's what I mean by Gaga for coherent sheaves. So in some sense, you can conflate the coherent sheaves on the scheme and on the analytic space because they carry the same information. Okay, so of course there was more to be said about the case of a point, but let me move forward to the relative situation, and some of the things, the finer points of the theory over a point will come up as we go along. So the relative version, well, there's different stages of relativization. The sort of first step that you would take from perfectoid fields is to go to perfectoid rings, or more precisely, perfectoid Huber pairs. So let RR plus be a perfectoid Huber pair of characteristic P. And I won't try to remind you what a perfectoid ring is, but in characteristic P, it's basically a perfect Huber, well, my Huber pairs are always going to be complete for the complete and separated. So you want to think about a perfect Banach algebra in characteristic P. That's basically what R is. If you don't remember about R plus, you can kind of ignore it for the moment. So you can define, so using the relative version of A-inf, so instead of taking OF here, if you put R plus, you can kind of make a similar picture. You again take out stuff that's fixed by Frobenius. Oh, and I should also say that my Huber pairs, by assumption, include a topologically nilpotent unit. And for notational purposes, I'll fix one and call it var pi, but nothing really is going to depend on that choice. It's just there to write some formulas down. So if you have, if you've made some choice like this, then you can do the analog of this construction where you take spa of a_nth and take out the parts that are fixed by Frobenius, and then you can divide by Frobenius. You can form what I'll call X sub R, and it's, well, you can form first the XR analytic and then XR by taking the bundle O of 1 again and taking sections. So you again have a comparison between these two things, but I would like to say, and use a similar technique to prove that one has Gaga for coherent G's, but there's a catch. So certainly it's okay for vector bundles. But coherent sheaves are hard to work with on spaces like this, which are heavily non-Noetherian. So this is going to be an issue going forward that, right, if you just think about perfect rings in characteristic P, those are almost never Noetherian. So there's I give this lemma to graduate students sometimes in my algebraic geometry class. If you have a ring of characteristic P in which the Frobenius map is a bijection, then the only way it can be Noetherian is if it's a finite product of fields. So essentially, unless you're dealing with points, perfect rings in characteristic P are never Noetherian. So that sort of propagates to saying that these spaces are also not Noetherian unless R is. So, so there's a problem with dealing with coherent sheaves when you don't know that everything that you're going to write down is a priori finitely generated, if you found it inside something else that's finitely generated. But for vector bundles, this doesn't tend to be an issue because right, you sort of avoid any issue of supports when you're working with vector bundles by assuming everything is locally of constant rank. And so it turns out vector bundles you can control, and you can operate the analog of the proof of Gaga for coherent sheaves, which basically involves first showing that O of 1 is ample on the analytic version. So for example, in this context, you need to show that given a vector bundle, if you twist it by a large enough O of n, then it can be generated by global sections. And so there's some argument, which is essentially an explicit calculation, to show that, in fact, that is the case for vector bundles on this thing. And then you can use that to show that, to realize vector bundles here as coming from here, and so on. So there is a satisfactory comparison of vector bundles. So in the published article by Liu, you can find this story for vector bundles. But if you want to do homological algebra calculations involving vector bundles, you don't tend to stay within the category of vector bundles. You tend to need some abelian category containing that. And so at the end, maybe I can, if I have a few minutes at the end, I'll say something about how this can be finessed in the world of vector bundles. But let me not get to that just yet. Let me tell you about some things that I can talk about just in the language of vector bundles on these things. So one is an interpretation of local systems on perfectoid Hooper pairs in terms of this. But maybe I should, before I do that, I should mention that this picture globalizes. If S is a perfectoid space, so a perfectoid space is an adic space that's made up of pieces that are the spectra of perfectoid Hooper pairs. So you can glue the analytic construction to make what I'm going to call XS. And now it's redundant to put analytic here, so I'm just going to call it XS. So you can make an analytic gluing of the relative Farg-Fontaine curves over different affinoid pieces. This is sort of dependent. Why is it possible to do this? So what I'm using here, so there's a natural morphism say in this context. So XR is in some sense fibered over the spectrum that I started with, but not in the category of adic spaces. This is a morphism of topological spaces. And it's only a morphism of topological spaces, not adic spaces. So it's clear that it can't be a morphism of adic spaces because on this adic space p equals 0, and in this adic space p is invertible. So these things are mismatched. So it's not the case that this can literally map to here, keeping track of the structure sheaves, but on level of underlying topological spaces there is a map, and this map in fact has a little more structure. So I like to call it sharp because it has something to do with the map that's called sharp in the theory of perfectoid spaces, which amounts to so if there were really an algebraic, if there were really a morphism here, that would correspond to some map of rings from R to, say, XR and. Yeah, sorry, I'm doing this at the level of analytic spaces, so I should put and here. So that would have to somehow come from a ring map from R to W of R plus, maybe with some things localized. Well, this comes from the existence of the Teichmüller map from R plus to W over R plus, which is only multiplicative. So it's kind of a bizarre feature of this story that this map from R plus to W of R plus is only multiplicative. It's not a ring homomorphism, and yet when you set things up the right way, it actually behaves as if it were a ring homomorphism in the sense that it can be used to define this geometric map, at least on the level of topological spaces. So there is some very meaningful sense in which the relative Farg-Fontaine curve, defined with respect to R, is in fact fibered over the spectrum of R. And when I talk about fibers, there is a base change compatibility. So if I have another, say, R1 plus here, and I make the construction like this. So there are genuine horizontal arrows, and there are these fake vertical arrows, which only exist at the level of topological spaces, but the diagram commutes as a diagram in the category of topological spaces. So it does make sense, for example, to pick a point in this spectrum and base change, say a rank 1 point. It makes sense to base change to that point, and then you get back the construction that we defined for a field. So there is this construction does behave like a fibration, whose fibers are these kind of mysterious curves. But you have to be cautious when you actually work with them because this structure morphism does not have such an obvious interpretation outside of topological spaces. There is this very pretty property that if you choose, right, so in perfectoid spaces there's this notion of tilting that turns arbitrary perfectoid spaces into characteristic P1s, and if you give me a lift of this to a perfectoid space over QP, then that defines a section of this, which actually is genuinely defined in the world of adic spaces. So there are lots, so this map, in some sense, has lots of sections. Well, if you conflate this thing with the spectrum of some untilt, you do get a morphism back up, but that's still a little bit funny because you have to identify this space with some other spaces that are naturally isomorphic to it as topological spaces. Okay, so I want to emphasize the fact that this construction, I know how to make base change, so I can talk about fibers. And so in order to make the next, so that allows me to do this gluing because you have a compatibility with base change, and say open immersions correspond to open immersions here, so you can glue. So you can talk about perfectoid. You can talk about the curve over a perfectoid space. You can also go to stacks on the category of perfectoid spaces of characteristic P perfectoid spaces, such as what Scholze calls diamonds. These are a little bit like passing from schemes to algebraic spaces, except the topology is different. I'll say something about the topology in a moment. So this notion of stackifying the construction will come up rather seriously when you start trying to write down moduli spaces of vector bundles, which is what you end up doing if you want to study geometric forms of the local Langlands correspondence, a la Farg and Scholze. It'll come up in a less serious way when I'm talking about local systems, which I'll do in a few moments. Local systems on things that are not perfectoid spaces, like rigid spaces. But let me say something about local systems on perfectoid spaces to set that up. So theorem, there exists an equivalence of categories here I'm going to take étal QP local systems on my perfectoid. So S is a perfectoid space right now. Now, I don't assume you know exactly what I mean by this. You could sort of guess, but I'll come back and fill in more precisely what I mean by this. Right? You can imagine, well, if I could take a ZP local system and then formulate, right, by kind of taking some inverse limit of truncated Z mod p to the n local systems, and then just think of that as extending scalars to QP. That's one way to think about things, but it's not the best way in this context. We'll see why. So this. Well, let me say it this way. So there's a full embedding, and I'll tell you the essential image in a moment. But first, let me tell you the full embedding. The full embedding goes from QP local systems on X to vector bundles on XS, and the functor is, roughly speaking, sharp upper star V tensor over QP with the structure sheaf. So this is some sort of symbolic representation, which I need to unpack. And I'm about to tell you the essential image, but let me postpone that for a moment. So I'll fill in the blank here in a moment. But before I do that, let me unpack a little bit what I've written so far. So first of all, QP local systems. So you can think of them somehow locally as arising from ZP local systems. So a ZP local system you can think of as, well, I take a right? You think of this as the inverse limit of z mod p to the n for all n, and each of those is a, you take a bundle, you view that as a z mod p to the n as being a sheaf, a ring sheaf on S, and you take a module for that which is locally finite free, and then you take some inverse system of those things, and then you kind of invert P in the Hom sets. However, that does not give you everything that you want to consider, because that gives you things that have a global lattice. And there are plenty of natural examples of local systems that one wants to consider that do not have a global lattice. So you need to localize to avoid assuming the existence of a global lattice. So there are all sorts of the examples that we most care about are things like period morphisms, where you don't, things that come from period morphisms where you don't get a global lattice. So it's very important that you allow for there to not be a global lattice. But if you're coming to the subject for a first time, I can give you a much more concrete example of a local system that doesn't come with a global lattice. Namely, if you take an elliptic curve with bad reduction and you take its Tate uniformization, so this is an elliptic curve, and you take a Tate uniformization by GM mod Q to the Z, then it's, to write down a vector bundle on here amounts to writing down an equivariant vector bundle for the translation action. And well, you could do the same sort of thing that I did before with O of 1. You could take the trivial bundle on QM, and then the effective translation is multiplication by P, or some non-trivial power of P. And that will give you something, that gives you something that lives on here in the world of analytic spaces, but does not come from the world of schemes. So we do of course want to think about such objects, as I said, because period mappings of the sorts that we saw several of last week give rise to constructions of QP local systems that do not have global lattices. So a lot of the interest in this topic is this kind of local system. So it's actually a good thing that this category includes objects like that. Okay. But I should say you can automatically incorporate this by sort of doing something in a more intrinsically perfectoid point of view, which is to introduce some version of what's called pro-étale topology. So there are several versions of the pro-étale topology floating around in the literature. I'm going to be working with the most restrictive one, where you sort of augment the usual étale topology with infinite towers of finite étale surjections. So this is sort of the minimum you need in order to be able to take the sort of inverse limits that you want to take is you need the étale topology plus things that are obtained from some given base by making a series of finite étale coverings. So this is, as I said, the most restrictive version of the pro-étale topology for perfectoid spaces that you will find in the literature, but this is sufficient for our discussion. So when you work with this kind of pro-étale topology, in this topology, you can construct a locally constant sheaf directly associated to QP. Yeah, so the opens are, you start with, you first make an étale covering, and then you build an infinite tower on top of that. I mean, you can also, there's a little lemma that says if you then put an étale on top of that, you can kind of right, that étale, you can sort of realize that at some finite level and kind of shuffle things around so that you put things back in canonical form. Yeah. Exactly, the pi1, right, the natural notion of the étale fundamental group, even of a rigid analytic space, is not quasi-compact. So this was originally observed by de Jong long before anybody was thinking about perfectoids. But this was already, I mean, there were already examples of period morphisms like the Lubin-Tate period morphism where this issue arose, that the natural pi1 you want to consider is not profinite. You're sort of forced to take that definition because you have these examples of QP local systems that you want to consider that do not have lattices, because this period mapping constructions force those upon you. So, yeah. So this idea that the pi1 is not profinite predates the notion of a perfectoid space, but we're using it in the same context. Right, so in the world of pro-étale topology, you can directly construct a locally constant sheaf QP. So the idea is if you sort of take an open in this topology, then the sections of this are something like continuous morphisms from the underlying topological space to this topological space. I should put the bar here. So there's a general notion of a locally constant sheaf on perfectoids associated to any topological space whatsoever. So here I'm using the topology of QP, and then of course it has a topological ring structure, so it promotes. And so then these are really just, so then these things are just locally, these are just QP underscore modules on the pro-étale site, which are locally finite free. So this is the notion one actually works with when kind of in this perfectoid world, as you just think, well, QP is a ring sheaf, and so I can just work with locally finite free modules over this ring sheaf, which is somehow what you wanted to do all along. Okay, so now I can put the bar in here and explain this notation. So what is the functor doing? Well, so what the functor is doing is it's taking a QP local system on S, and it's producing a QP local system on XS, which I'm then tensoring up to O. And the thing that I'm producing on XS, I'm writing it as phi, as sharp upper star, because, okay, it's not the case that this morphism, that's not me, is it? Okay. Okay. Is it okay with, is the mic still okay? Great. So this is not a morphism of adic spaces, it's only morphism of topological spaces, but it also has some compatibility with pro-étale coverings. So it turns out there actually is a well-defined pullback functor from QP local systems on here to QP local systems on here. And so that is what I'm using to define the functor. So again, if you just sort of squint and imagine that this arrow is filled in, then you just think it's pullback, but it's not literally pullback because that doesn't make sense. Nonetheless, you can still define the pullback functor. Okay, and now finally I should tell you the essential image. So the essential image is, well, there's the, what I write down here is sort of forced by the case of a field, but it's non-trivial to show that this is actually, everything of this form actually works. So I'm going to be, the essential image consists of the vector bundles, which fiber by fiber are semi-stable of degree 0. So, right, I told you there's a notion of degree for vector bundles, so that gives you a notion of semi-stability. A vector bundle being semi-stable means it has no proper non-zero subbundle of strictly larger degree, just like in classical vector bundle theory. And one of the main theorems about vector bundles over a point in this context is that the ones that are semi-stable of degree 0 are exactly the ones that come from Étale local systems. So this sort of reinterprets a statement that's been floating around in p-adic Hodge theory for a long time, but it puts it in language that sounds more like something geometric. It sounds more like the Narasimha and Chaudhuri theorem. What's the trouble with his name? So that theorem that tells you about vector bundles on compact Riemann surfaces, the ones that are semi-stable of degree 0, correspond to representations of the, well, maybe the stable ones of degree 0 correspond to irreducible unitary representations of the fundamental group. This is some kind of geometric version of that over a point, and the correct condition to put in this context is just to put the condition fiber by fiber, and then the non-trivial thing you have to add to the previous theorem is you have to add the fact that, well, you get local systems fiber by fiber, that they somehow actually fit together. So there's some extra work involved to show that the local systems that you get on individual fibers actually interpolate. Yes? In the relative group, what is the Picard group? Right, so last week we talked about the Picard group of the curve, and we said that over a geometric point, the Picard group is just Z generated by O of 1, and otherwise you pick up the morphisms from the Galois group to QP star. So if you work in this context, you get a similar statement. So rank 1 things are automatically stable, so you can just read off the same conclusion. The Picard group will be the copy of Z generated by O of 1, and then the contributions of things that are degree 0, and those will be the continuous homomorphisms from pi 1 to QP star, just like before. Okay. So what I want to do in the last, how many do I have? I have about 15 minutes. So what I want to do with the last 15 minutes is to talk about how you use this framework to say anything about local systems not on perfectoid spaces, but on spaces that we have a more intrinsic interest in, like rigid analytic spaces. So how does this... So how does this apply to rigid analytic spaces? Well, if, say, S is a rigid analytic space over QP, let's say, then I can define, again, a pro-Étale topology over S, again, by augmenting the Étale topology with towers of finite Étale surjective morphisms. And this has a neighborhood basis of affinoid perfectoid spaces. Now, to actually make this statement precise, you have to be a little bit more careful than I'm being. Let me draw the picture. So the picture that I have in mind here, if say S is itself affinoid, then you could build a finite Étale cover of S1 and a finite Étale cover of that and so on, in such a way that the tower has some kind of the inverse limit is, well, it's not technically a perfectoid space because inverse limits behave a little bit poorly in this context, but there is a notion of the inverse limit is similar to an affinoid perfectoid space. And the way you're supposed to think of this is if this is SPA of some ring A0, then this would be SPA of A1, A1, and so on. And you're sort of taking the thing at the top is going to be some sort of completed direct limit of the ANs. And the issue is, what do you mean by the completion? Well, if you're careful about norms, you can define a completion here. But that involves some extra data which is not present in the topological picture, so that's why you have to be a bit cautious. But roughly speaking, this is the geometric analog of the way we go, so compare, right? The usual thing that we do in p-adic Hodge theory is we want to think about representations of the Galois group of QP, but we don't have any kind of structure theorem for the Galois group of QP, so we go up along, say, the cyclotomic tower. So you get this algebraic extension up here, and if you complete it, then you get a perfectoid field. So after completion, this is a perfectoid field. And so it has a tilt, and the Galois group of this thing is the same as the Galois group of the tilt. So classical phi-gamma module theory comes from the fact that, well, okay, so this group, this cover is Galois with Galois group ZP cross. So the way you think about representations of QP in terms of phi-gamma modules is you think about representations of the Galois group of the smaller field, which you can then interpret in terms of the tilt and use phi module theory there, and then you keep track of the fact that there is a residual Galois group that should act on the picture. So the representations of QP correspond to representations of this smaller, of the Galois group of this smaller field, plus descent datum for the residual Galois group. And so this construction is meant to be analogous to making this passage, except in this context, there's not a canonical choice of what tower to use, so you somehow work with all possible towers. So by working with this pro-étale topology and thinking of these special towers as being some kind of neighborhood basis, it gives you the possibility to incorporate things like descent data in a very natural way. So descent data will be replaced by sheaf conditions. So for example, if we talked about the spectrum of QP, and I wanted to talk about a QP local system over the spectrum of QP, or even a ZP local system, I could work with some object up here, and nominally I would have to keep track of descent data, but as long as I argue that I'm working with sheaves on the pro-étale side of QP, then that automatically imputes the descent data. So I don't have to carry around something like gamma separately. In this business, the role of something like gamma in classical phi-gamma module theory is played by the fact that you have a topology on the pro-étale side associated to the original space, and the sheaf property for sheaves on this pro-étale site sort of takes care of that kind of descent data. So I'll talk about, when I define things like relative phi-gamma modules, there's no gamma in the picture. The gamma is some kind of vestige. It appears in the notation for kind of psychological comfort, but there is no gamma explicitly on the board. It's hidden. Its role is being played by sheaf conditions. So this is an important psychological point that I think is, well, I mean, it's important to use this language of phi-gamma modules in order to give people a way to transition into this subject, but you know, there is no spoon anymore. Okay, so now how can I talk about cohomology of local systems in terms of this? Well, so it's a little bit awkward. So I would like to say the following, that étale QP local systems on S correspond to vector bundles on the relative Farg-Fontaine curve over S. And I mean, if you interpret this statement appropriately, it's true. It's just you have to think of this is only valid in some stack theoretic interpretation of XS. So so there's no direct notion of a Farg-Fontaine curve over SPA of QP, for example. What you have is for every one of these perfectoid subdomains in the pro-étale site, you have a Farg-Fontaine curve over that, and you can talk about bundles over that. And then if you want to talk about the Farg-Fontaine over curve over S, you have to think of it as some sort of stack. And then you have the vector bundles on a stack are vector bundles on the cover plus the descent data. So the descent data is sort of showing up again in a hidden way inside this adjective, stack theoretic. So when you talk about a stack, when you interpret XS, X is not a perfectoid space, there's a stack theoretic construction going on, and so there is some descent data implicitly there as well. But given it's natural to make this interpretation, and once you do that, then formally you can transfer that statement to a statement that says that the étale QP local systems correspond to certain vector bundles on XS, namely the ones that when you base change from S to any perfectoid point, or even a geometric point would be enough, you get something which is semi-stable of degree 0. Yeah, I should have pointed out that one of the things that's not obvious in the story but follows from the classification of vector bundles over points is that this notion is stable under base change from one field to another. So you could make this check on the level of geometric points, for example. Okay, so now you can encode vector bundles into some kind of into some vector bundles on a sort of a stack theoretic Farg-Fontaine curve, and you can now prove something like theorems like. So let me give you a sample theorem that comes out of this, and this is maybe where I'm going to end up. Except we'll see the coherent objects at least at a point, and then maybe I'll mumble a few words about what happens away in the relative case. So. So say you have S over, S is a rigid analytic space over a field, and say V is a QP local system in the de Jong sense, say, then what can I say about the, so I'm going to consider the pro-étale cohomology of it. So when I write HI, I'm going to mean cohomology for the pro-étale topology. This sort of the thing you want, it corresponds to some sort of continuous cohomology in a more naive language. But this is what you naturally compute with. And so what can I say about the groups HIV? Well, so one thing that turns out to be true is that if K is a finite extension of QP, these turn out to be finite dimensional QP vector spaces. I just want to make sure that I'm actually copying this. Yes, if I'm working with, yes, if K is finite extension of QP, these cohomology groups are finite dimensional QP vector spaces. Oh, sorry, S is smooth and proper. I should have said this from the outset. So if you, we might see this later. So if you look at, say, the trivial local system, then I think one knows something like this without the proper hypothesis. I think maybe Alberto is going to say something about this. But I'm going to require smooth and proper because I want to use the Cartan-Serre construction, as I'll say in a moment. All right, that's my 5-minute warning, sounds like. So the other case that you want to consider is what happens if K is algebraically closed. And then what happens in this case, there's still a finiteness statement, but you have to state it a little more carefully. These groups are what are called Banach-Kolmez spaces. So roughly speaking, they're like finite dimensional over K plus or minus finite dimensional error terms over QP. So sometimes, in some cases, you can show that there's no contribution from K. So for example, if you have something that actually has a lattice, then you can show that there's no contribution of K, but this can genuinely fail. This can genuinely fail to be finite dimensional over QP. There are various examples. So for example, I think you get some examples out of the work of Kolmez, Dospinetscu, Nisiel. But you can actually write down kind of easy examples from Tate elliptic curves, for example. But there are kind of interesting examples that come from Drinfeld upper half plane, for example, where you have this only this weaker finiteness statement is true. Okay, so why does this basically comes from showing that if I take this morphism and give it a name, if I call this thing F, F push forward carries vector bundles on XS into coherent sheaves on XF. Or maybe I should say RIF lower star. So basically, when you have a smooth proper morphism, you have what's called the Cartan-Serre construction. So the Cartan-Serre construction, geometrically, it's like this. So when you have a proper object, it means that there are lots of ways to cover it by aphanoids. So for example, just for the purpose of the picture, let's say S was P1. So P1, of course, can be covered by two disks with some overlap. And you could take a really big overlap, or you could take another covering that has a much smaller overlap. And on one hand, these are both aphanoid coverings of the same space, so they give you the same cohomology. However, if you directly compare the complexes that could compute the cohomology, then restriction from the ring of functions on this big disk to this ring of functions on this smaller disk is what's called a completely continuous morphism. It's sort of, if you write things out in terms of power series, then the contributions from the sort of high order terms are very, very small. So the comparison, so because you have something proper, you can compare lots of covers like this, where this thing is what's called an inner subdomain of this thing. And using that, you can make some kind of general argument that shows you that you get some kind of finite dimensional answer, except of course, you have to work in an abelian category. So you don't necessarily land in vector bundles, you only land in coherent sheaves, and that in particular potentially gives you, and in fact, in examples, actually gives you this kind of phenomenon, where the cohomology of coherent sheaves on XF turn out to be not finite dimensional over QP in general. They're only Banach-Kolmez spaces. And so when you make this kind of calculation, you're very naturally thrown into this environment because you can only hope to get something, you can only hope to make a statement whose target is an abelian category because homological algebra doesn't respect exact categories in general. Right. So these coherent sheaves on XF, these are the sorts of things that one wants to call coherent. Well, if X were not algebraically closed, if I started, sorry, where F, I should have said F is the tilt of K in this case. So if F is the tilt of K, then I'm getting coherent sheaves on XF. Well, what about if K is finite? Well, I can go to a perfectoid overfield, like going from QP to the cyclotomic extension, and do the same thing, and then what's left over, well, it will be a sheaf on XK in the stack theoretic sense. And so those coherent sheaves on XK, or X, are the things that I want to call coherent phi gamma modules over a point. So they're basically these are objects that we've seen before. These are they have other interpretations in terms of modules over the roboring or B pairs and so on. But these are sort of a natural envelope of the category of usual phi gamma modules. And so one of the things that we're trying to do in the subsequent work is to basically come up with a good notion of coherent phi gamma modules, not just on the far front, not just over a point, but actually over a general rigid space. And this is much subtler because although S itself is a Noetherian adic space, these perfectoid coverings of it are not. And so a great deal of caution is needed in order to manipulate coherent sheaves when you're actually writing the sections down over these non-Noetherian spaces. Roughly speaking, what happens is the descent data, it being defined with respect to some Noetherian space, the descent data is what kicks in and gives you good properties like the ascending chain condition and so on. But this is a rather deep story, which I'm not going to say anything more about right now. So I'll just stop there. Yes? It would be, I don't think so, because I mean, right? You want to make something that's a stack relative to some category, and if the category is going to be a category of adic spaces, then, right? If you have some adic space which is not, I mean, not all adic spaces can be kind of represented by schemes. Not even all perfectoid spaces in characteristic P. So there are perfectoid spaces of characteristic P that you would want to consider where there's no, that space is not itself naturally represented by some scheme, and so the Farad-Fontaine curve over it should also not correspond to some scheme. So as long as you stick to bases which are affinoid perfectoid, then there is a ring in the picture, and so its spec is in the picture. So you can hope to do a schematic construction. But in the long run, it's the adic construction that really shows up most prominently. Like when you talk about diamonds, you've totally lost the schematic construction. Yeah, so when S is a point, what I'm using here is, right, the fact that the vector bundles, which are semi-stable at degree 0, are the ones that correspond to Galois representations. This is a consequence of the Farad-Fontaine classification of vector bundles, or equivalent forms of it in my work. But yeah, but there is, as I mentioned, there's quite a bit of extra work required to doing this because a priori, the vector bundles that you get fiber-wise do not fit together. So you have to you have to sort of write down the functor from right to left. So right, it's clear that the functor from left to right has to have essential image landing in this category because the construction commutes with base change to a point, but it's not so obvious that you can go from right to left. And that's somehow where the extra work that we had to do shows up. Can you extend this to CP local systems? Well, you can write down the functor from left to right, I suppose. And then I'm not sure what happens after that. I have not really thought about that, I should say. So you have like, you're thinking of something about CP representations of GK, where K is finite over QP, and kind of comparing those to something else. Yeah, that I would imagine that's, yeah, that sounds something like relative Hodge state theory, which one knows something about, but I'm not sure maybe we should talk about it offline. You could, in principle, work with some fairly arbitrary, say, analytic adic space, where you assume something like, well, you need something like some residue characteristic P condition, but you could put that in. Yeah, the one issue that shows up is if you start to try to talk about these coherent phi gamma modules, you really want this space to be at least Noetherian. But you could imagine, I guess maybe you're imagining something like the complete eigencurve with its boundary put in or something, which is no longer over QP. Yeah, that's an interesting kind of example that it doesn't technically fit into what we're doing. We actually do use at various points the fact that we are working over QP to, for example, show that semi-normal rigid spaces embed faithfully into diamonds. This statement shows up. But yeah, it should in principle be possible to work with some more general, at least Noetherian adic spaces here. But our work does not directly extend to that setting. There actually would have to be some more technical work done. I think it's doable, but it would not be entirely straightforward. So what I'm really considering is, yeah, this is, I guess I'm considering the cohomology on XS. Yeah, but as a stack theoretic object. Yeah, that's sort of what naturally corresponds. So in the classical situation over a point, the fact that agrees with Galois cohomology is some fancy reinterpretation of Herr's theorem, or really Herr-Liu, right? It's sort of, right? It's essentially the statement that Rochuan proved in his thesis that you can interpret cohomology of QP representations in terms of the analog of the Herr complex, but in the world of phi gamma modules over the Roper ring. So essentially, that's the statement that says that when you do this over a point, you're getting the same thing that you would have gotten from. I mean, if you do this for a local system, you're really actually computing the right cohomology.